Our first step in looking at the spring mass system is simply to understand or get some intuition about how the behavior of this mass is affected by various properties of the system. What our target is going to be is to understand x in this case. And x in words here is going to be the displacement away from the equilibrium. And what that means is if we have the spring and we have our wall and we have the mass attached there, if the spring is at its natural extension, then the x would be 0. And then if we stretch out the mass, so we move it a bit further out, it'll be stretched. And as soon as that happens, it's going to start moving back towards the equilibrium. But as we know from having seen, swings and springs like this, it's then going to return and double back. It's going to go too far, it's going to overshoot, and then it's going to be pushed back in the other direction, then pushed back, and we're going to get oscillations in the end. In terms of differential equation speak, though, what we're going to be looking for is x as a function of time. So the position of the mass over time. If we knew what that was, we'd be essentially prediction. It would be a prediction of the future position, knowing all that we know about the system itself and how it maybe started moving. So x of t is going to be our goal. We want to find that because it's the prediction of how the system would behave if we let it go its own way. Now, what's underlying all this? Some very nice simple physics. So if we imagine our mass, and we've got our position here, let's say that's 0, and here's x, the actual position of the mass, then the spring is going to be exerting a force on the mass. There's also going to be two other forces, which are fortunately balanced out. There's going to be a gravity force and a normal force, but because the mass is simply sliding back and forth, the normal force and the gravity force are going to cancel out all the time. So in the end, the only force that's going to be acting on this mass in a nice idealized world would be the spring force. There might also be friction. We're going to ignore that for now. So simply a spring force is the only force applied horizontally to this mass. Now, we're going to just try to do some mental experiments here. So imagine we have a very, very, very tightly coiled spring here, and we have sort of a loose, springy spring. The very stiff example would be this one here, and then a non-stiff or a loose spring would be this one down here. The way we're going to model the force is as a spring force with a constant k. So F spring is going to be a k times the displacement x. And if that's the case, then if the spring is stiff, this is our displacement, so how far we stretched out the spring, and this is the spring constant. That's what changes if we swap out springs. And as we look at those two elements, what we can think of is, well, let's stretch the spring the same amount and ask which spring has a larger force. So if we stretch this spring out a certain amount and this spring out the same amount, well, we expect the force to be much larger if we have this tightly coiled spring or the stronger spring. So that's going to have a larger k value because for the same displacement, I multiply by a bigger number to get a bigger force. And correspondingly, if we had a loose spring or a soft spring, then we'd expect that the k value would be smaller because for the same displacement, there's less force, so it's multiplied by a smaller number here. Now, again, to build our intuition, we're going to talk about the period of oscillation. So again, that's the time it would take to complete one full cycle of the oscillations. So if we compress the spring, then let it go, and then let it come back to where it started, we'd measure that time. That would be the period. If we increase the stiffness, then what do we expect to have happen there? Well, I think if we have a stiff spring, we expect the mass to get pushed more rapidly, or there's going to be a larger force that motivates the spring to move. And so we expect to get faster cycles, or the period should decrease. if we increase the stiffness. So if we increase K, notice that's what that is. K was our stiffness, and if the stiffer the spring, the larger the K, then we expect the period to decrease. Meanwhile, if we increase the mass, so we actually go from a small mass to a large heavy mass, well, we'd expect this smaller mass to have less inertia, and so it can be more effectively pushed by the same force. So if the spring's the same, we'd expect it to be pushed and accelerated more. And so in comparison, if we increase the mass, we expect it to take longer for a cycle, and so we would say the period would increase for this particular scenario. So as we change the design parameters, as we change the spring constant or as we change the mass, we expect different things to happen to the period of the oscillations. And that's good just to get an insight into what we expect in the math as we go forward. Now, can we narrow this down even further? If we know K and we know M, and we're going to assume that friction is negligible, here's the question: should we be able to determine the exact period? So in the last page we had some basic insight, but it wasn't exact. We just knew a rough relationship between the inputs K and M and the motion. Now the question is, should we be able to determine this exact period? Well, I think yes. There's nothing we do not know. If we have the spring constant and we know the mass, we should know pretty much everything there is to know about how this system's going to behave. But from the work so far, can we easily find the formula, and actually not in principle, but actually in practice here? The answer is going to be no. We can't get a formula from what we've seen so far. And so that's going to be where we head next. What we've seen here is that we have an intuition about how this system should work. We should get oscillations, the spring should move, or the mass should move back and forth. There's not a lot of physics or math going on so far. However, there's really no way from what we've seen so far to predict critical features. In other words, how long is it going to take for this mass to move back and forth once? We don't have that information, but we should be able to get to it. We know that there should be a way. And so what we need are some new tools to look at this problem. And with those new tools, hopefully we can, in a non-obvious way, be able to do that prediction of critical features.